Hi, my name is Janine Bijstebos and welcome to this second part of this talk that's part of the FSL course about probabilistic functional modes or PFMs. This is the second part of a talk of 3 parts, so if you haven't listened to the first part that went into the PFM framework and its key features, then I would recommend having a look at that first. In this second part, we're going to look at PFM network matrices, particularly in comparison to ICA or independent components analysis, and talk a little bit more about interpretability of functional connectivity and caveats with that. Just a quick reminder, PFM is an analysis that we can perform on resting state fMRI data to extract in a data-driven way resting state networks. And so in this talk, I'm going to refer to networks, components, and modes a little bit interchangeably. And these terms all conceptually represent large-scale patterns of co-activations or resting state networks in the brain. The term networks is a more generic term. The term components comes from independent components analysis, where the outcomes are described as components. And the term modes comes from probabilistic functional modes, where we describe the outputs as modes. So let's get started with part 1, which is about network matrices that we get from PFM and how they compare to results from ICA. If you haven't heard about the term of network matrices or NetMats before, there's an earlier lecture or set of talks in the FSL course about FSL nets, which explains this idea, this term in a little bit more detail. So if you haven't listened to those earlier talks about FSL nets, it might be helpful to go back to those first. So what I'm going to talk about here is 2 different types of network matrices or NetMats. In general, the idea of a NetMat is that it's looking at interactions between pairs of networks or components or modes. So for every pair of networks, we want to have a single number that describes the interaction between those networks. And we can use 2 different types of information for doing that. First of all, the temporal NetMat, or the temporal network matrix, uses the time courses, or more specifically the correlation between the time courses, to define the NetMat. So we have 2 different components from ICA or modes from PFM we extract. We have the time course for each of those from our analyses, and we look at either the full correlation or more commonly the partial correlation to determine our NetMat. Alternatively, what we can also do is look at the spatial network matrix. Now, this is less commonly used in the literature, but the idea is that instead of using the time courses from the components and relating those time courses to each other, here we're using the spatial maps from the components or the modes and actually vectorizing all of the voxels along one long line and then just doing the correlation between 2 spatial maps. And what that represents, as this figure is showing here, is it represents the amount of overlap that you see in terms of the weights in the spatial map between a pair of modes. So in this figure in the black, it's showing the same component in blue for each of them, the visual cortex, and then it's showing 4 different components overlaid on that in orange. And the numbers, the R values at the bottom, describe the correlation that you would observe if you did what I just said and do the spatial correlation between these components. So it goes from quite a lot of overlap on the left-hand side to very little overlap on the right-hand side. One of the main reasons why we don't see spatial NetMats a lot in the literature is because spatial ICA, which is the most common application of ICA in fMRI, doesn't allow for estimating spatial network matrices. And that's because there's the independence constraint, which is a requirement for ICA, which has to be implemented either in the spatial domain or in the temporal domain. More commonly, it's done in the spatial domain because we have more voxels and therefore more degrees of freedom in the spatial domain. And so what that means, as you can see in the top left of this figure, is that there are no correlation patterns between pairs of spatial maps of ICA components because they're forced to be independent of each other. This doesn't necessarily mean there's no overlap at all, and there's a paper from Christian Beckman that shows that in probabilistic ICA, in the presence of noise, you can still have a little bit of overlap between networks, but it cannot be captured in this way by looking at the correlations, because it's effectively the noise is hiding those correlations if there is any overlap that can be determined. In temporal ICA, it's the other way around, as you can see on the bottom right of this figure. Now you're enforcing the impedance constraint in the temporal domain, and so there's no temporal network matrix structure. And so this is an interesting thing to think about, because essentially with these different applications of spatial versus temporal ICA, you're pushing the information of the interactions between the different networks either fully into the temporal NetMat or the temporal domain, or fully into the spatial domain, depending on where this independence constraint is enforced. And so that was one of the goals with developing PFM, is to remove the independence constraint, so that the model doesn't require independence either in the temporal domain or in the spatial domain. And as a result, the findings that you get from Profumo or PFM sit somewhere in the middle, where you can see here is a group average temporal network matrix on the left and a group average spatial network matrix on the right. And so you can see it finds substantial overlap spatially between networks, but there is also weaker but meaningful temporal interactions between networks. So let's move on to the second part of this talk. We're going to look a little bit at what types of spatial maps we get from PFM and from ICA, and how they compare to each other and how that interacts with dimensionality. This is a figure that shows 6 different components or networks. The top line of the figure is the result from Profumo or PFM, and the bottom line of this figure is the result from ICA. And these are lined up so that they're maximally matched. And you can see for this analysis, and this was a relatively low dimensional decomposition, asking both ICA and PFM models to give us 25 networks, you can see that there's really remarkable consistency between these two different algorithms. And this is to some degree really interesting to see, because we've changed the cost function, the algorithm, and the priors quite a bit between PFM and ICA, and yet you find really remarkably similar components. Of course, you can see some differences here. So for example, in the 5th component here, you can see that PFM has more extensive weights for this mode in the lateral parietal cortex, and they're a little bit lower for ICA in that same region. But visually speaking, and also quantitatively, these networks are a really good match between the two approaches to resting state fMRI analysis. It changes a little bit when you go to higher dimensionalities. So now, instead of asking both ICA and PFM to get 25 components, we're asking the models to give us 150 components. So it's essentially a finer grain decomposition. And here the interesting thing is that there is still some one-to-one matching. So this figure here on the left-hand side, we see again one mode from PFM at the top and a single mode from ICA at the bottom. And again, there's really good one-to-one matching in that particular component. But for some other components within the 150 that we're going to get, we see a one-to-many mapping, where we have a single component from Profumo, here shown at the top in from three different views, and that breaks down into 6 different components in ICA, seen here at the bottom. And so you can see that different parts from these components map onto each other. So for example, the posterior cingulate is captured in just a single component in ICA and is part of this more elaborate component in PFM, and a few other examples here as well. This is really interesting, and this is a function of the independence constraint that we're enforcing on ICA, where if we're asking ICA to give us 150 components, because components have to be spatially independent of each other, it wouldn't be able to find such a kind of spatially large, extensive component as PFM is identifying here. And instead it starts kind of breaking that bigger network down into subnetworks. So it's still explaining the same amount of variance, it's still capturing that network as a whole, but like I said, it's breaking it down into subnetworks. And Profumo doesn't have the constraint of requiring networks to be independent of each other. And so it is still able to, if the data supports it, identify this network as a single network. So in the third part of this talk, I want to delve a little bit more into the interpretability of functional connectivity and some caveats with that. And I want to highlight a few ways in which PFMs differ from ICA that were intended to address some of the challenges with interpretability. And this is really about spatial versus temporal variability in the brain. So as you've already probably seen from the previous slides, it depends a lot on the algorithm in terms of whether variance in the original resting state fMRI dataset gets assigned or represented in a spatial way, like either in the spatial map or in the spatial network matrix, or in a temporal way, such as in the time course or in the temporal network matrix. And we've previously shown that if you have variability across subjects in terms of the spatial organization of networks, that the model isn't very good at capturing and representing, then this can actually systematically bias the estimation of functional connectivity, or specifically of the temporal network matrix. It's useful to realize that this bias isn't necessarily a problem if your main goal is to do prediction. So if you're taking all of the outputs from either ICA or PFM and using them as features to predict behavior, then you're probably going to get very similar results because the variance is kind of included in both of the models. But the problem is in terms of interpretation. So if you have spatial variations that are not accounted for appropriately, then they're kind of misrepresented or misattributed to temporal variations. And so if you're trying to interpret the mechanism of what is driving the behavior that you're looking at, for example, then that misattribution can change or impact your interpretation of the results. And so I'm going to delve a little bit more into two different types of spatial variations and how they might influence the results. One is about misalignment, and the second one is about overlap between nodes. So in any functional MRI analysis, whether it's resting state or task fMRI, every pipeline that does such analysis aligns subjects to each other and usually also to standard space, because the goal is to compare subjects at the end of the day, either between a group of patients and a group of controls, or to look at continuous associations with a certain behavior. And so we want to make sure that we're comparing apples to apples and oranges to oranges and aligning subjects well. It's well known that those algorithms are not perfect. Registration and alignment is a very challenging thing to do. There's a lot of topological variations across subjects that are difficult to account for. So you see residual differences. An example is shown here. So this is a functional region that might extend a little bit more medially in some subjects than in other subjects. Or the posterior cingulate cortex being a little bit enlarged and closer to the midline for one subject versus another subject. And the important thing is that if your modeling approach is not accounting for these individual differences in alignment, then you can bias the estimates for temporal network matrices. And the reason for that is that if we're not getting the boundary right of where a region sits or a network sits within a person, where it's kind of shifted compared to the actual ground truth organization of that person, then the time series that we will extract from that is kind of a mixture between the network that we were aiming at and something else that's around it. And so if the time series that we feed into our network matrix are a mixture, then that's obviously going to impact the correlations that we see with other time series, which might also be mixture. So the network matrix becomes more and more difficult to interpret. And there's two features in the PFM algorithm that are aimed at addressing this issue. One of them is explicit subject modeling. So instead of having a completely separate group model in ICA and then a post hoc dual regression approach to map the group maps back onto the individual, PFM involves explicit modeling of single subject data, and also this hierarchical optimization where it optimizes group level maps and then it goes back and optimizes the subject level maps. So both of those elements are aimed at addressing or at least improving this issue. And so the question that you might ask is how good is it at doing this? This is a comparison between PFM in orange and ICA dual regression in green. And these are simulation data. So the advantage of simulation is that you can systematically vary or control the amount of misalignment that occurs in a data set. And so you can see that on the horizontal x-axis where the exact percentages are not super important, but it goes from less misalignment across people to more misalignment across people. So the challenge for the algorithm of being able to capture accurately the individualized organization becomes more difficult from left to right. And then on the y-axis is the association with ground truth again, because these are simulations. We actually know the ground truth spatial map that we fed into the data set. And so the higher up, the closer to one these violin plots are, the better the model is doing at capturing those ground truth organization. And so you can see that in almost in all cases, Perfumo is outperforming dual regression. Dual regression doesn't do badly in many cases, but Perfumo does even better and gets even closer to one in many cases. This is a visual example just to kind of give you a little bit of intuition for the sorts of misalignment that you might see. And this is in relatively high quality Human Connectome project data. So it's a little bit hard to see, and I'll guide you through it, but there's a black outline shown here, which is the same network in the same individual subject, but from a different type of scan, a different version of alignment that was used. And then in the color underneath it is the network from, again, a different alignment. So you can see that these are the same networks, but they're kind of slightly offset from each other. So this line here of the yellow and red color doesn't line up with this line here of the black network. And so this is a sort of example of realistic amount of misalignment that we might see even in high quality data sets. And then this example, this result here at the bottom is showing how well ICA deals with this. So this is not even PFM, which outperforms ICA, but this is ICA. And so in this case, the blue outline is now driven by the colored mapping here. So the blue outline is the ground truth of the organization for this network, and now the colored map here is the result that we get from ICA dual regression if we drive it by this network here. So you can see it's not perfect, there are some areas where it kind of spills out of it a little bit, but overall kind of this shift that we've seen here has been completely recovered, and you can see that the ICA results are doing actually really quite well in terms of capturing this misalignment. So the next topic that I want to discuss a little bit more is spatial overlap. And so here in this figure at the top here, we're showing one network in green and another one in red. And you can see that there's a relatively large amount of overlap between these networks. And importantly, individual subjects might differ from each other in terms of the amount of overlap. So they might be kind of more overlapping, as you see here in some people, and then kind of more separated and adjacent to each other rather than overlapping in other people. This is challenging for algorithms or models to distinguish, and particularly for independent components analysis, because as you remember, there's the independence constraint. And so these here at the bottom are some results from a paper that we wrote a few years ago, effectively showing that these distributions are temporal NetMats distributions. And so the ground truth is in blue. And then you can see that in ICA, in this case of overlap, you get a shift or a bias towards higher values in the network matrix because it's not able to represent this overlap due to the independence constraint. And so again, PFM has a few features that are really aimed to try and address this challenge. One of them is to drop the independence constraint and allow for both spatial and temporal overlap or correlation or association between modes. And the second one is using a structure of priors to encourage correspondence between the group level solution and the subject level estimates, because at the end of the day we want to be able to compare like the default mode network across everyone. So we need to have, rather than just extracting networks completely separately for each subjects, we want to have some kind of correspondence to, again, make sure that we're comparing apples to apples across people. But then we also want to make sure that the model kind of hierarchically gets a good chance to have a good estimate of the individualized organization. And so the prior structure and the kind of hierarchical optimization structure within PFM is designed to try and address this. Again, these are some results. So it's the same type of figure with PFMs in orange and ICA dual regression in green. Here along the x-axis, instead of varying the amount of misalignment across people, it's varying the amount of overlap between modes. And so again, the challenge for the model kind of becomes progressively harder as there's more overlap. So it becomes harder as we go from left to right. And on the y-axis, it's shown a correlation to the ground truth, where values closer to 1 are better at recapturing the ground truth. And so the results are showing us that PFM is capable, more so than ICA dual regression, to handle or disentangle network overlap, although you can see that it gets more difficult as there is more extensive network overlap. This is a video from, so it's showing two different networks. It's showing one network on the left-hand side, top and bottom, and a second network on the right-hand side. And this is kind of cycling through a population. So it's showing as we move across a behavioral continuum from more negative traits like substance use to more positive traits like a higher IQ and higher self-reported life satisfaction. It's showing how these two networks kind of change in their shape and organization and layout. And this was, when we first found this was really surprising to us, because whilst we knew that there was residual misalignment across people, the assumption that we had was that that was relatively random. And so we were very surprised to see that those kind of residual differences in functional organization after registration across individuals was really strongly and systematically related to behavior. And so one question is, why is this? Why does it matter that this network kind of morphs a little bit further downward? Why is that important for behavior? What is the mechanism in which that might influence behavior? And so we looked into this a little bit more. I'm showing the same video here across the same behavioral continuum, but in this case it's looking at summed weights across all networks or across all modes. So in this case it's essentially looking at network overlap. Areas where you see more yellow and brighter yellow show more overlapping organization across different modes or networks. And so the answer to why does it matter where a network exactly sits is because it's not just that in that network, there's probably another network that also moved in towards it, and so there's actually more information in the spatial network matrix. There's more extensive overlap between networks, and that seems to be the thing that is driving this association with behavior. That's just to say that this is not just a like technical description of like, oh, models can be better or worse at capturing this type of overlap, but there's a real kind of implication for the fact that this might be very important for behavior, and so it's something that we want to make sure that we model and that we're able to kind of interpret appropriately. This slide summarizes that a little bit more. This is using canonical correlation analysis, or CCA, which is a way of kind of looking at the similarity between a feature set on the one hand side and a feature set on the other side. And higher correlations here mean that there's kind of more shared information between those feature sets. And so you can see that the line that's the highest here is this dark blue line, which is ICA temporal network matrices compared with PFM spatial maps. And so that's to show that a lot of the information that is represented temporally in ICA is actually represented spatially in Perfumo. I should emphasize here that we don't know what the ground truth is. I mean, when we do the simulations that I've been showing on the previous slide, they can be very useful because they give us some control over the ground truth. But when we're analyzing real brain data, we don't know what the ground truth organization is. And so we hope the idea behind developing PFM was that it would be more accurate because it's less constrained. And so we hope that PFM is a more accurate representation of brain organization, but it's hard to know that for sure. And the other thing that I always like to remind myself of is that there's probably not one single ground truth kind of network organization in the brain, because the brain is highly dynamic, it's hierarchically organized, and so it might kind of cycle through different states across time, and you can probably accurately reflect the network organization of the brain at multiple different hierarchies. So when we, at the start of this part, when we talked about 25 dimensionalities or 25 networks versus 150 networks, those you can probably describe the kind of organizational principles of the brain accurately at both of those scales, because it's a hierarchy and that's how it's organized. Here's a little bit of a summary of all of the things that I've talked about today. PFM is designed to overcome potentially some of the limitations of ICA by dropping the independence constraint, modeling the group level and the subject level at the same time, kind of hierarchically optimizing those two solutions. And so yeah, if you're interested in studying resting state network organization, then I would encourage you to try out PFMO or PFM and learn a little bit more about it. Thank you so much.